Hi everyone, I'm Julia, the chemistry tutor. Today I am going to talk about Lewis dot structures. And the method I'm going to take is first we're going to do a little tiny bit of recap on something I talked about on the periodic table. Then we're going to look at how to do Lewis dot structures. We're going to go through polarity and how to tell if your molecule is polar or nonpolar. And then we're going to talk about VSEPR, which is molecular structure. Okay, and so then I'm going to do some practice and do Lewis dot structures with all of that information. Okay, so let's get started. Okay, so remember when we were talking about the periodic table, we were talking about when ions form and when atoms gain and lose electrons, and the whole reason for that is because they want to have the same electrons as a noble gas. Okay, because noble gases are perfect. They want to be perfect like the king. They want to be the nobility. Okay, so that is why our ions form. Okay, so when we're not forming ions, when we're forming covalent compounds between a nonmetal and a nonmetal, then we're going to be sharing electrons. Instead of losing and gaining and giving away our electrons, we're actually going to share electrons, okay, to make it seem like we have that same as the noble gases, okay? And so let's talk about the valence shell, your valence electrons. Okay, your valence electrons are the outside shell, your outside energy, your outside layer of electrons, right? So when we're talking about the valence, we're talking about the highest energy level. Okay, so by now you've already done your electron configurations. Okay, so if I were looking at the electron configuration for oxygen over here, so oxygen, I've got 1s2, 2s2, and 2p. He's got 4 electrons in his p, 2p. Okay, so his valence electrons are the highest shell, and your highest shell is shell number 2 here. Okay, so he's got 6 valence electrons in his highest shell. Okay, so let's look at magnesium over here. Okay, so magnesium has 1s2, 2s2, 2p6, and 3s2. Okay, his highest shell is 3. He has 2 electrons in his valence shell. Okay, so let's look at bromine over here. Okay, so bromine, I'm going to erase this because I'm going to need some space for bromine. Okay, so bromine has 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember your D's right here are 1 energy level lower, so that's 3d10, and then I'm back over here to 4p, 5 electrons to get to bromine. Okay, so our highest shell here is shell number 4. So he's got 7 valence electrons in his outside shell. Okay, so notice I didn't count those. The D's don't count because those are 1 shell lower. They are not valence electrons. They're not your highest energy. So we will never count the D electrons as valence. And likewise, we're never going to count the F electrons as valence. Only the S and P electrons are your valence electrons. Okay, so what I want you to notice is bromine here. We said that bromine has the 7 valence electrons. We'll look at bromine's group number. He's number 7. Okay, we said that oxygen here has 6 valence electrons, and look at oxygen's group number. It's group number 6. Okay, if we look at magnesium here, we said magnesium had 2 valence, and look at magnesium's group number. He's group number 2. Okay, so remember, we start over on a shell, that outside shell, as soon as we hit a noble gas. So we always start counting over. So all of these have 1 valence, 2, 3, 4, 5, 6, 7, 8, just like your group number. Okay, and what that 8 means is that everybody wants an octet. They want 8 electrons in the valence shell. Okay, remember, they want to look like the nobility. They want to look like a noble gas. Okay, so the octet rule is they want 8 electrons in the valence shell. except hydrogen. Hydrogen is perfect with 2 electrons like helium. So hydrogen gets 2 electrons. Okay, maximum. Hydrogen does not get an octet. Helium does not get an octet. Everybody else on the periodic table gets an octet, 8 electrons in the valence shell. Okay, so let's talk about what all of this means. Okay, so Lewis dot structures are a method of looking at how a nonmetal and another nonmetal, how they share electrons to form a bond to form together into a compound, into a molecule. Okay, so we draw a structure, and from that structure, we can tell if the molecule is polar or nonpolar, if it's going to be soluble in water. If it's polar, it's soluble in water. We can tell what its shape is going to be. And from that, we're not going to get into it too deeply if we were to be looking at allied health chemistry, but general chemistry, you'll get a little bit more into it. Okay, so let's take a look at what we're talking about, the rules for Lewis dot structures. Okay, so I'm going to go through these rules a couple of times, working through a couple of structures to just apply each rule to each structure. And some of your instructors might have a little bit of a different method. They might have you counting like valence electrons, how many needed, how many available, dividing by numbers. I don't do it that way. Okay, if your instructor does it that way, you can do it that way. You can also do it my way. It works either way. Okay, some instructors have you do it where you put the dots in and then draw lines between the dots. I don't do it that way. I just form bonds. So your instructors, if they have you putting the dots in, very, very soon, they're going to have you just putting the lines in like I do. Okay, so the first one I'm going to work on is we're going to do CH4, which is methane. If you're in organic chemistry, you would have to know the name for that. Okay, in general chemistry, you typically don't learn the names for those. Okay. Okay, so first thing we have to do is count our valence electrons. Okay, so if we look at our periodic table, carbon is in group number 4, so he has 4 valence electrons. Hydrogen is in group number 1, so each hydrogen has 1 valence electron. So I have a total of 8 valence electrons. Okay, so then we choose our central atom. Okay, if carbon is there, carbon will always, always be the central atom. Okay, and hydrogen, because hydrogen can only ever have 2 valence electrons, and each bond is 2 electrons. That means hydrogen can only ever have 1 bond. Hydrogen can never have more than 1 bond. So hydrogen cannot be a central atom because a central atom has to have 2 things bonded to it. 2 or more. Okay, so hydrogen can never be a central atom. So when we look at CH4, we know carbon is in the center. Okay, so I'm going to put my carbon down. Okay, now I'm going to bond my atoms to each other. So I take a hydrogen and I bond them in, and a hydrogen, and a hydrogen, and a hydrogen. You're going to use 4 sides of your molecule. Okay, no more than 4 sides, and you are going to use 4 sides. Okay. So we bonded our atoms together. So now we're going to count the number of electrons that we used in the bonds to see how many we have left. Okay. Well, I used, that's 2, 2, 2, and 2. So I used 8 electrons. So I have 0 left to use. Okay. So I don't have any leftover electrons. So I'm going to skip rule 5. I don't have any left over from that. I'm going to skip rule 6. I don't have any to share. I'm going to skip rule 8. Now I'm going to check my number of electrons in my structure to make sure I have the correct number. And we kind of already did that. We have the 2, 4, 6, 8, and we had 8 valence electrons. So that is our structure. Okay. And the next one we're going to work on is CO2. And you have or will be learning the name of that. That is carbon dioxide, 1 carbon, 2 oxygens. Okay, so we're going to count our valence electrons. Carbon on our periodic table is group 4, and oxygen is group 6, and we have 2 oxygens. Okay, so we have 16 valence electrons. Okay, so we're going to choose our central atom. Again, carbon is there, so it's going to be in the middle. But if it were not carbon, let's say it were sulfur instead. Okay, atoms that are multiples are always on the outside. Okay, so example, if I had SO2, oxygens are on the outside, sulfur's on the inside. Okay, so that oxygen would be on the outside, those oxygens in CO2, and carbon's going to be in the middle. Okay, so we're going to put our carbon in the middle. Now we're going to bond our atoms to each other. Okay, so I have two oxygens, so I'm just going to put them on two sides. Okay, so I've got my two oxygens there. Okay, my next rule is count the number of electrons that I used in bonds. So I've got two here and two here, so I've used 4 electrons. Okay, so to determine how many we have left. Okay, so how many we have left? We've used 4, sorry, we've used 4 electrons. We have 12 remaining for lone pairs. Okay, these are also called unbonded electrons. Unbonded electrons and lone pairs are the same thing. I'm going to start using LP for lone pairs. Okay, so I have 12 electrons left to use for lone pairs. Okay, so the rule is we place leftover electrons as lone pairs on the outside atoms first to fill their octet, to make sure they each have 8. Okay, so I'm going to put 2, 4, 6 on that oxygen. Now that oxygen has 2, 4, 6, and that bond gives him 8. And I'll put 2, 4, 6 on that oxygen. Okay, so there's my 12 electrons that I had left for lone pairs. I put 12 more electrons in there. Okay, and both of those oxygens have octets filled. They both have 8 electrons. Okay, but carbon, if we look at carbon, he only has 4 electrons around him. Okay, so carbon doesn't have an octet. So we're going to have to give carbon an octet. And the way we do that is if we had any electrons left over, we'd put them as lone pairs on the central atom, but we used those 12 up in lone pairs, so we didn't have any left over to put on the central atom. Okay, so now we're going to share electrons to form double or triple bonds if necessary to fill the central atom's octet. Okay, so I'm going to take a pair of electrons. I'm going to take that pair of electrons right there. And I'm going to move them down here into a bond. Okay, so those electrons now are no longer there, and it is now a bond between carbon and that oxygen. Okay, so but now carbon still only has 6 electrons, so he still needs 2 more electrons. Okay, so you might think, okay, well, I'll just share another pair, that pair right there, move them on over there and form a triple bond, because you can have a triple bond. It's possible to have a triple bond. Okay, that's a maximum you can have, is 3 bonds between 2 atoms. Okay, but chemistry loves symmetry. Okay, so instead we're going to take those 2 electrons right there, move them over here, form a bond there, and now carbon has an octet, and both oxygens have an octet, because we just look at it in terms of oxygen has his 8, this oxygen has his 8, and carbon has his 8. Okay, they're sharing electrons. That is a covalent bond, right? Like cohabiting, to be together, to share things. Okay, so that is covalent. Okay, the other way that we know that we're not going to share both lone pairs from one oxygen is because down here is what I call the honk rule. Okay, hydrogen is really, well, hydrogen only ever gets one bond. That is the deal. Okay, oxygen is most stable, most happy with 2 bonds and 2 lone pairs. Okay, oxygen prefers 2 bonds, 2 lone pairs. Nitrogen, 3 bonds and 1 lone pair, and carbon, 4 bonds. So I remember honk, 1, 2, 3, 4. That's how many bonds they want. And then you fill in their octet with lone pairs. Okay, if he has 2 bonds, that's 4 electrons, so he would have 2 lone pairs for his other 4 electrons. If he has 3 bonds, that's 6 electrons. 1 lone pair gives him his other 2 electrons that he needs. Here, 84 bonds is 8 electrons. There's his octet, and hydrogen gets his 2 electrons, his 1 bond. Okay, so we know from the honk rule up here, if we had shared that lone pair from oxygen, from both of them from the same oxygen, okay, neither of those oxygens are happy. Oxygen wants 2 bonds and 2 lone pairs. Neither one of them have 2 bonds and 2 lone pairs, so neither one of those are stable. Okay, so we know that this one, because here oxygen has 2 bonds, 2 lone pairs, 2 bonds, 2 lone pairs, 4 bonds. Okay, just like they like it. Oh, and some of your instructors, if you're in Gen Chem, they're going to talk about doing formal charge to determine which structure is correct. And I'm not going to go into that in this video. If you need some help with that, email me and set up a private session. I'd be happy to help you with that. Okay, now I'm going to do CH3Cl. Okay, so first we're going to count our valence electrons. Carbon has 4. Each hydrogen has 1, and there's 3 hydrogens. And then chlorine is a halogen. He has 7 valence electrons. So I have 14 total valence electrons. Okay, so we're going to choose our central atom. Okay, carbon will always be in the middle. So I'm going to put carbon in the middle. I'm going to bond his atoms around him. So I'm going to give him 3 hydrogens and a chlorine. Okay. Count the number of electrons used in bonds. So we have 4 bonds, 2 electrons per bond. So I've used 8 electrons. Okay, so I still have 6 for lone pairs. Okay, so we're going to place the leftover electrons around our outside atoms first. Feed the kids first. Okay, well, hydrogen, each hydrogen already has 1 bond. Hydrogen's got their 2 electrons. You cannot put lone pairs on hydrogen. Okay, so we're going to put 2, 4, 6 around the chlorine to give chlorine his octet. Okay, and carbon already has his octet. So carbon's got his octet, hydrogen's got his octet, chlorine's got his octet. Okay, there's no electrons left over to put on the central atom. We don't need to share any electrons to form double bonds. Okay, so now we're just going to count our electrons and see if we have the correct number. So I've got 2, 4, 6, 8, 10, 12, 14. I had 14 valence electrons. I think I forgot to count those on the last one. So I do that sometimes. I forget to count at the end. Okay, so it's just like I had the CH4. Just instead of an H, we have the chlorine on there, and we've got lone pairs around the chlorine to fill his octet. Okay, so remember I talked about that honk rule down there, okay? So you follow those rules if possible. Sometimes it's not possible. Sometimes you cannot follow those rules and you just have to do what you have to do. So I'm going to do a couple of examples when you can't follow the rules. Okay, one of them here is carbon monoxide, 1 carbon, 1 oxygen. Okay, count my valence. I have 4 for carbon, 6 for oxygen. So I have 10 valence electrons. Okay, there is no central atom because there's only 2 atoms there. So we're just going to bond them to each other. Okay, so count my electrons that I've used. So I bonded my atoms, count my electrons I've used. I've used 2 electrons. So I have 8 left for lone pairs. Okay, so we don't have any outside atoms to put them on, right? Because we put them on our outside atoms first. Okay, so we're just going to split those evenly among those 2 atoms. Okay, so I'm going to put 2 lone pairs, which is 4 electrons on carbon, and 2 lone pairs, which is 4 electrons on oxygen. Okay, so you'll notice both of those only have 6 electrons around them. Okay, oh, I don't have any left over to put on central atoms, right? I don't have any of that happening. Okay, so none of them have an octet, so I need to form octets. Oh, sorry, I do have some of these. I need to share electrons to form double and triple bonds if necessary. Okay, so I'm going to take a pair from oxygen and I'm going to share it down to the middle and form a bond there. Okay, but you'll see still they both only have 6. Neither one of them has an octet. So now I'm going to take from carbon, right? Because we're going to be symmetrical in this. I'm going to take from carbon, I'm going to take a pair from carbon and move it down there. and form a bond. Okay, so now you will see they each have 8 electrons because I have 6 right here, plus these 2 is 8, plus those 2 is 8. Okay, so they both have an octet. But you'll notice the honk rule is not followed. Remember? Oxygen likes 2 bonds, carbon likes 4 bonds. Okay, well, we can't do anything else. There's nothing else we can do about this. We have to go with that because it's the only thing that we can do. That is the structure for carbon monoxide. But that's also part of why carbon monoxide is so reactive and dangerous in our bodies, is because carbon is looking for anything else to bond with, and oxygen's looking to dump that other bond. Okay, and it's shaped a lot like carbon, a lot like oxygen. So our hemoglobin bonds it really tightly. So carbon monoxide does not follow the honk rule. Okay. Okay, now I'm going to do ozone, which is O3. Okay, count my valence electrons. I have 3 oxygens, and each of them has 6 valence, so I have 18 valence electrons. Okay, so to choose a central atom, well, there's only oxygen there. Oxygen has to be in the middle. So we're going to bond those 3 oxygens to each other. Okay, count my electrons used. I have 2 bonds, so I've used 4 electrons. I have 14 left for lone pairs. Okay, put them around my outside oxygens first. So there's 2, 4, 6, 8, 10, 12. So I still have 2 electrons left. And in that case, any electrons left, we put on the central atom. Okay, so we're going to put a lone pair on the central atom. Okay, so you'll notice that central atom does not have an octet. Both of the side atoms have octets, but the central atom does not. So one of those oxygens is going to have to share a lone pair. So I could take it from this oxygen, move it down here, and put it there. Or I could have taken it from this oxygen and put it there. Okay, it could have gone either way. That's what we call resonance, is when either one of them could do it equally. It basically flops back and forth between the two. Okay, so I'm going to get rid of one of those because we don't want them both on there. I don't want to confuse you. Okay, so you will notice that these 2 oxygens don't have their 2 bonds and 2 lone pairs like they like. This one's happy, but the other 2 are not. Okay, so this is part of why ozone is so dangerous, is because not all of them have what they want, the 2 bonds and 2 lone pairs. Okay, so if at all possible, follow that honk rule. If not possible, then you just can't follow it. Okay, and I didn't mention halogens tend to like 1 bond and 3 lone pairs. Okay, so typically like the CH3Cl that I did earlier, that chlorine, that halogen, had 1 bond and 3 lone pairs. Okay, halogens tend to like it that way. Okay. Now I'm going to talk about polarity and intermolecular forces, how to tell if a polar is molecule and what its intermolecular forces are. Okay, so intermolecular forces, inter connects 2 different molecules to each other. So it's like what would make one water molecule be attracted to another water molecule. Okay, intermolecular forces, like an interstate connects 2 different states to each other. Okay, so intermolecular forces connects 2 different molecules to each other. Okay, and from that we can tell if it's polar or nonpolar. Okay, so the first one is, and these are, by the way, in order of strength, your strongest intermolecular force is up top, your weakest is on the bottom. Okay, so your ionic force is the strongest, and you know it's ionic if it has a metal and a nonmetal, because that defines ions, right? Ions are metals with nonmetals, right? The cation has lost an electron, the anions gained electrons. So you know if there's a metal there, the intermolecular force is ionic. You don't even need to think about it, okay? So your second strongest force is if you're hydrogen bonding. And it's when you have a hydrogen bonded directly to a nitrogen, oxygen, or fluorine. Those are your 3 most electronegative atoms. We talked about the periodic table, and electronegativity gets higher as you go up and to the right on the periodic table. Noble gases don't count. So nitrogen, oxygen, or fluorine are the three that are up furthest to the top and the right on the periodic table. Okay? And they have to be bonded directly to a nitrogen, oxygen, or fluorine. So like if I had this guy, that does not hydrogen bond because I don't have hydrogen bonded directly to that oxygen. Okay? So if I had instead done this, now yes, that does hydrogen bond because I have a hydrogen bonded directly to an oxygen. Okay, so hydrogen bonding is when you have a hydrogen bonded directly to a nitrogen, oxygen, or fluorine. And by the way, those are polar. If it's hydrogen bonding, it is polar bonds. Okay, so your next strongest intermolecular force is if you're dipole-dipole, and that's if you have a polar molecule. Okay, and we're going to talk about this a little deeper in a second here, but you know it's polar if you have at least one polar bond. And it is non-symmetrical. It has to be both polar bonds and non-symmetrical. Okay, and you can tell if you have a polar bond because your difference in electronegativity is 0.5 to 1.9. Okay, we're going to talk about what that means in a minute here. Okay, and I can just tell you this caveat right here. If there's a lone pair on your central atom, your molecule is polar. Absolutely. Lone pairs on central atom, molecule is polar. So like if you had NH3, which you know is polar already because it's hydrogen bonding, but it's also got the lone pair on that nitrogen, that makes it polar also. Okay. So, and then if you're none of those, if you're not ionic, if you're not hydrogen bonding, and you don't have polar molecule, your only choice left is London dispersion forces. These are also called van der Waals. Some instructors call those van der Waals forces. Okay, but most instructors either call them London or dispersion or London dispersion. Okay, and that's when you have a non-polar molecule. Okay, and that's when all of your bonds are non-polar and or, it doesn't have to be both, either non-polar bonds or you have a symmetrical molecule. Okay, and a non-polar bond is when your difference in electronegativity is 0 to 0.4. Okay. This is the electronegativity chart. When I had talked about earlier that electronegativity, right, it gets larger as we go up and to the right. Okay, and ignore those. Don't worry about those. Okay, so see your nitrogen, oxygen, and fluorine are your three most electronegative atoms. Okay, so one thing about this chart, okay, some instructors don't use this chart. They just go by is it symmetrical or non-symmetrical. Okay, some instructors go by this chart. But what I want you to recognize is we don't care about, well, we do care about hydrogen, but we don't care about any of these numbers because those are all metals. And we know if those are there, that is an ionic compound. We don't even need to go any further. We don't need to determine is it hydrogen bonding? Is it polar? Is it non-polar? We don't care. Okay, so I'm going to put hydrogen over here just for our purposes. Hydrogen is 2.1. Okay, so we really only care about those. Okay, so even if your instructors don't use this chart, it's pretty easy. So remember we had said that a polar bond is when your difference in electronegativity is between 0.5 and 1.9. If it's above 1.9, there's a metal there and it's ionic. Okay, and a non-polar bond, so a non-polar bond is when you're 0 to 0.4. Okay, so I just remember 0.5. If it's 0.5 or greater, it's polar. If it's less than 0.5, it's non-polar. Okay, and even if your instructor doesn't use this, it's pretty darn easy to memorize. Okay, so if you look here and remember fluorine starts at 4, you drop by a half as you go left. Okay, and then you drop down by 1 and drop by a half, not quite a half and not quite. So those maybe, okay, some students say that's hard to memorize. I just remember that sulfur to phosphorus is not quite, it's 0.4, and then phosphorus to silicon is 0.3. Okay, so 0.5 difference here, 0.4 difference here, 0.3 difference here. Okay, And then we drop down by just 0.2, and then it's a difference of 0.4 and 0.4. Okay, this drop was 0.2. We dropped by 0.2, 0.3 here, and then that difference is 0.4. We don't really use these a lot. You're probably never going to use astatine. I doubt you're ever going to use tellurium. You might use iodine, okay, but mostly we use carbon, nitrogen, oxygen, hydrogen. Oh yeah, hydrogen is 2.1. Hydrogen and phosphorus are the same. That's how I remember phosphorus actually, that drop is 0.4 and then the next one is 0.3, because I remember hydrogen is 2.1 and phosphorus and hydrogen are the same. Okay, so we might use silicon, but we'll use phosphorus, sulfur, your halogens. Maybe selenium and arsenic, but not very often. Usually it's the carbon, nitrogen, oxygen, hydrogen, your halogens, phosphorus, and sulfur, typically. Okay, so those aren't too bad to memorize. Some of your instructors will give you this chart. Okay, so looking at this chart, if I had, just going to leave those undone. So if I were doing, let's see, I'm going to make that a little bit smaller. Okay, so if I were doing that CH4 that I did earlier. Okay, my carbon is 2.5 and my hydrogen is 2.1. Okay, so my carbon 2.5, hydrogen 2.1. That difference is 0.4. Those are all nonpolar bonds. That's a nonpolar molecule. Plus it's symmetrical. It's exactly the same all the way around, so it's nonpolar. Okay, so I had done the one that was CH3Cl. Okay, so we have the okay, my carbon, my hydrogen, and my chlorine. Carbon is 4. Hydrogen is 2.1. Oh, sorry, carbon's not 4. Ooh. Carbon is 2.5. Hydrogen is 2.1, and chlorine is 3.0. So carbon to hydrogen, 0.4, those are nonpolar, but carbon to chlorine is 0.5. That's a polar bond. Okay, and our rule is it has at least one polar bond and it is not symmetrical. Okay, and so it's not symmetrical. It's not exactly the same thing all the way around. So that is polar. Okay, and I want you to keep in mind, if I had this, that is still not symmetrical. Okay, because our molecule is actually not flat on the table. Okay, it's not symmetrical. If I were to draw this like it's actually shaped, and we'll talk about shapes in a minute here. Okay, if I drew that how it's actually shaped, I would have like a hydrogen, I would have a chlorine, hydrogen, chlorine. Okay, so do you see how that is not symmetrical? If I were to draw an arrow towards the more electronegative atom, ooh. Okay, those arrows would go to carbon. See how I've got more arrows pointing down? It's not symmetrical. They don't cancel each other out. Okay. So if it's non-symmetrical and has at least one polar bond, it is polar. Okay, and think of one. Oh, here we go. So if I had CH3Br, okay, same structure. Okay, so you're going to say, oh, it's not symmetrical, it's polar. And some instructors will let you get by with that. Okay, but if they have you do the numbers, we know carbon hydrogen is 0.4. So we've already decided carbon hydrogen bonds, nonpolar bonds. But carbon is 2.5 and bromine is 2.8. That difference is 0.3. That's a nonpolar bond. There are no polar bonds in this molecule. That is a non-polar molecule because there are no polar bonds in there. Even though it's non-symmetrical, There's no polar bonds. It's a nonpolar molecule. Okay. And let me do one more quick example for you of something that you're going to think is, well, I don't know if you do the numbers. So pH 3 is this guy. Okay. Phosphorus is 2.1 and hydrogen is 2.1. That difference is 0. Those are absolutely nonpolar bonds, but it has a lone pair on the top. If it's got a lone pair, it's polar. No matter what, it is polar. It's got a lone pair on it. That makes it polar. Okay. Okay, so there's a couple of times that you might think it's symmetrical or think it's non-symmetrical, or okay, so if your instructor has you looking at electronegativities, look at your electronegativities. If there's at least one polar bond and it's non-symmetrical, it's a polar molecule. Okay, let me do one more quick one here. If I had done that, remember I had the CH3Cl. Well, what if I had CCl4, carbon tetrachloride? Okay. If we did the Lewis dot structure for him, and we'll get a little more detail on Lewis dot structures in a minute here. Okay. We already said that a carbon-chlorine bond is polar, but that molecule is symmetrical. They all cancel each other out. If I were to draw those arrows toward the more electronegative atom, they all cancel each other out. Okay. So even though those are polar bonds, you have a symmetrical molecule that's a nonpolar molecule. Okay. Okay, now we're going to talk about VSEPR, which stands for valence shell electron pair repulsion theory. Okay, so the valence shell electrons, right, the ones we're looking at that are involved in your Lewis dot structures, electrons are negative, so they repulse each other, they push each other away. Okay, so we're looking at the shape that's formed in a molecule due to those electrons pushing each other away. Okay, so this is really just molecular shape is all VSEPR means, is what is the shape of your molecule. Okay, so if we go down here and look, I've got those CCl4s, the carbon tetrachloride that I had done earlier. Okay, well, this is how we drew it in a Lewis dot structure. This is how it's really drawn. Okay, and this one right here means that that's coming out of the board at you, and this one is behind you, the board behind you. Okay, so these electrons here are pushing away those electrons there, and these are pushing away all of those, and those are pushing away those, and those are pushing away those, and they're all pushing each other away. Okay, and so it's what shape is the molecule going to be to where all of those electrons are as far away from each other as they can possibly get. That is what VSEPR means, valence shell electron pair repulsion. Okay, and we are going to know from very specific things on what those are going to be. Okay, it's going to be based on number of groups of electrons around your central atom, how many of those are bonded atoms, and how many lone pairs it has, and that's going to help determine your shape. Okay, so if we have, I'm going to start at 4 here. Okay, so let me erase those. If I were drawing, okay, so if I'm starting with the 4 here, okay, if I have, let's do that. I'm just going to do the hydrogens on there, okay? And I'm not going to draw the dots, okay? One of those is coming at you and one of those is going away from you. I'm not going to draw the wedge and the lines, okay? So that's got 4 groups around it, okay? This up here is our electron geometry based on just electrons. What is its shape? If it's got 4 groups around it, it's tetrahedral. Okay, so that's tetrahedral in electron geometry. Okay, if we're looking at molecular geometry, okay, this one up here is how many lone pairs, how many bonded atoms and lone pairs. Well, if you've got 4 bonded atoms and 0 lone pairs on the central atom, your shape doesn't change, you're still tetrahedral. Okay, so if you've got 4 groups around you and all 4 groups have atoms bonded, okay, then you're tetrahedral, no matter what. Okay, but let's do ammonia here. So ammonia is this guy, okay? So if we're looking at how many groups does he have around him, and when I'm looking at groups, I'm looking at like how many sides of the atom is there stuff on. There's stuff on 1, 2, 3, 4 sides, okay? So he's got 4 groups around him. Okay, so for electron geometry, looking at just electrons, he's tetrahedral. Okay, but now if we're looking at the molecular geometry, when you're looking at a molecule, you can't see those lone pairs. Okay, you can't see lone pairs when you're looking at an actual molecule. So it no longer looks tetrahedral. It no longer looks like it has 4 things around it. Okay, so if you can imagine that one of these is coming at you and one of those is going away from you, that's a pyramid. Okay, it's trigonal, because it's got 3 things bonded to it, pyramidal. And some instructors might just let you write pyramidal. Okay, or they might want you to write trigonal pyramidal. Okay, but you can tell because that lone pair kind of pushes everything down into a pyramid shape. Okay, so now if I do water, okay, water, we draw it like this, okay? It's kind of like if I drew it like I had drawn those. So I would have my oxygen, hydrogen, whoops, hydrogen, hydrogen, and those are both lone pairs. Okay, so we don't put a line because you don't bond a lone pair. Okay, so see how I just kind of tilted it around a little bit and put it all in one plane instead of one coming at you and one going away from you. It's all in one plane, and this is one coming at you, one going away from you. Okay, so that's water. Okay, and it's got 4 groups around it, stuff on 4 sides, so it's tetrahedral in electron geometry. Okay, but it's got 2 bonded atoms and 2 lone pairs. If you got 2 bonded atoms and 2 lone pairs, it's a bent or angular, okay, because we can't see those lone pairs. And look, it just looks like a bent molecule, okay? And you are going to have to memorize these, okay? So then over here on the side is the bond angle. I'm going to talk about those others in a minute, but let's hit that bond angle. So some instructors say that's 109.5 degrees. 0.5 degrees, 0.5 degrees. And if you have lone pairs, they generally say it's a little bit less than, because the lone pairs up here actually push these down, so that bond gets that angle gets a little bit smaller than the 109.5. Okay, some instructors don't make you put the less than, so it's just totally up to your instructor and what your instructor is doing. Okay, but that's the angle between those atoms. Okay. All right. Okay, now looking at if we have 3 groups around us. Okay, so I'm going to do this guy. Okay, if you have 3 groups around you, you're drawn like that. And that's all in one plane. There's nothing coming at you and nothing going away from you. They're all in the same plane. Okay, and so if you've got 3 groups around you, your electron geometry is trigonal planar. Trig because it's got 3 planar because they're all in one plane. Okay. And this doesn't have any lone pairs on the central atom. All 3 of those are bonded atoms. So the shape didn't change. Your molecular geometry is also trigonal planar. Okay, now what if I had, I'm trying to come up with one. What if I had H, N, O, yeah, let's look at that guy. Okay, So nitrogen is your central atom. He's got 3 groups around him. So his electron geometry is trigonal planar. Oh, but if we draw him like he's actually supposed to be drawn, my nitrogen, my hydrogen, and my lone pair up there. Okay, if we're looking at molecular geometry, we can't see that lone pair. Again, it just looks like a bent molecule. Okay, so its molecular geometry is bent. Okay, and you'll notice you have 2 bent, but you know the difference in them because of their angles. The angles are different. Okay, and so to remember the angle for this, it's easy because it's all in one plane. It's just a circle. A circle is 360 degrees. If we divide a circle into 3 pieces, it's 120 degrees. That is your angle of the trigonal plane, or it's 120 degrees. It's a circle cut into 3 pieces. Okay. Okay, now our last option is if you have only 2 groups around you. Okay, so if we look at carbon dioxide here, carbon has stuff on 2 sides of him, is 2 groups. That is linear. And that is also all in one plane. There's nothing coming at you. There's nothing going away from you. It's all in one plane. It's linear. Okay, and you don't have an option to have lone pairs on a linear. You have 2 bonded atoms and no lone pairs. You're linear. Okay, because let's take a look. If that carbon had a lone pair here, there is no central atom. You have to have at least 3 atoms to have one be in the middle, to have a central atom. 2 is just a pair. There is nobody in the center, okay? So for linear, there is no option for lone pair. If you only have 2 groups around you, you're linear, okay? But don't forget to count lone pairs as groups, right? Like that nitrogen that I had a minute ago had that, and he had a lone pair on him. That is 3 groups, but 2 of them are bonded and 1 is non-bonding. 1 is a lone pair. Okay, and since this is linear, it's all in one circle. Whoops. It's all in a circle in one plane. If we cut a circle in half, my 360 degrees divided by 2 is 180 degrees. And that is what his angle is. On a linear, it's 180 degrees. The angle from here to here is 180 degrees. Okay, and up here on that lone pair, right, a little bit less than if you have that lone pair on there that some of your instructors have you do. Okay, so that's your VSEPR shapes, your valence shell electron pair repulsion theory. It's the shape of your molecule. Okay. Okay, so now we are going to practice a few of these, and I'm not sure what happened. It's a little bit blurry on the bottom there. I think when I scanned it, it didn't come through as well as I would have liked, but you can still see it. Okay, so we're going to start with that top one there, the CH2BRF. So first, we're going to follow our rules. I'm hoping, oh, sorry, I'm going to have to do this because apparently I didn't save it there correctly. All right. Okay, so if we're looking at the CH2BRF, okay, so first we've got our valence electrons, okay? So remember, we look at our periodic table. Carbon has 4 valence, each hydrogen has 2. Bromine has 7 because he's a halogen, and fluorine has 7, okay? So I've got 20 valence electrons there. Yep, I'm going to erase that so we can see what's going on there. I'll write it down here. 4 plus 2 plus 7 plus 7. Okay, so I've got my 20 valence electrons. Okay, so we're going to follow those rules. So if you didn't write down those rules, or you didn't take a picture of the screen and you don't have that, maybe go back and write down the rules, and maybe take a picture of the screen of the electronegativities. Okay, because we're going to be referring to those, and maybe take a picture of the screen of the VSEPR shapes because we're going to be referring to those as well. And I'm not going to be popping back and forth. I might pop back and forth a little, but I don't want to get too crazy with that. Okay, so we're going to choose our central atom. So carbon is always in the middle. We're going to put our atoms around them. So I'm going to give them a couple of hydrogens and a bromine and a fluorine. And it doesn't matter. I could have put the fluorine here and the bromine here, or I could have put the bromine on the other side. We don't care where you put it, as long as they are bonded to that central atom. Okay? So we chose our central atom, we bonded our atoms. Now we're going to count the electrons that we used in bonds. We have 4 bonds, so 2 electrons per bond. I've used 8 electrons, so I have 12 left for lone pairs. Okay, and we put them around our outside atoms first to fill the octet. Hydrogen already has his duet, so he's happy. So I'm going to put 6 around bromine to give him his octet, and 6 around fluorine to give him his octet. Okay. So now we're going to look at the VSEPR shape. Okay. So we're looking at the number of electron groups around that central atom. You've got 1, 2, 3, 4. So I've got 4 electron groups. So my electron geometry, remember, if there's 4 groups, the electron geometry is always tetrahedral. Okay, bond angle on tetrahedral is 109 or 109.5, depending on your instructor. Okay, how many lone pairs do I have on the central atom? None. Carbon is the central atom. He has no lone pairs. Remember, if you have no lone pairs, your geometry stays the same. No change. Okay. And now if we're looking at polar or nonpolar or an ion, it's not an ion because it's not a metal or charged. Okay. So we know that carbon, its electronegativity is 2.5, bromine is 2.8, and fluorine is 4.0. So that difference between fluorine and carbon is definitely polar. It's greater than it's greater than 0.5. So I have at least one polar bond, and it is non-symmetrical. So it is polar. Ooh. I don't know what's going on with my screen here today. Okay. And the intermolecular force, remember the intermolecular force, if you're polar, is dipole-dipole. Okay. And soluble in water. Okay, so I don't know if you've ever heard the term that like dissolves like. It means polar is soluble in polar, and nonpolar would be soluble in nonpolar. Okay, so if we're looking at water here, water is this guy. Lone pairs on the central atom, definitely polar. So anything that's going to be soluble in water is anything that is polar. Okay, so this is polar. It's soluble in water. Okay, guess I'll just write soluble. Okay, so now I'm going to do this next one down below that looks kind of scary because it's got so much stuff going on. But we're just going to follow our rules. Okay, so first we're going to count our valence electrons. So 4 for carbon, 1 for each of these hydrogens, so that's 3, 6 for oxygen, 5 for nitrogen, 1 for each of those hydrogens, so that's 2. Okay, so I believe that's 20 valence electrons. So I've got 20 valence electrons again. Okay, so now when it comes time to choosing a central atom, okay, there's more than one central atom here because all of those can't be bonded around one atom. You can only have 4 things around you, okay? So when this happens, we've written it out kind of like it's bonded. So we know that these 3 hydrogens are bonded to that carbon because they're written right behind the carbon. The oxygen is bonded to the carbon and the nitrogen, and those 2 hydrogens are bonded to that nitrogen. Okay, so it's showing you your bonding. Okay, so I've got carbon. I'm going to put 3 hydrogens around him. So his 3 hydrogens. Okay, and then he's bonded to an oxygen that's bonded to a nitrogen that has 2 hydrogens on it. Okay, Does that make sense? Okay, when there's a lot going on there, we write it out just like it's all bonded to each other, okay? So now we're going to count the electrons used in bonds. I have 1, 2, 3, 4, 5, 6, 7 bonds, 2 electrons per bond, so I've used 14 electrons. I have 6 left for lone pairs. Okay, we put them on the outside atoms first. But none of your outside atoms, they're all hydrogens. So none of those can get electrons. Okay, so now we're going to put them on central atoms. Okay, so I'm going to give 2 of those 6 to nitrogen and 4 of them to oxygen. Okay, so everybody has an octet. Everybody has their 8 electrons, and we're following the honk rule. Hydrogen has 1 bond, oxygen has 2 bonds and 2 lone pairs. Nitrogen has 3 bonds and 1 lone pair. Carbon has his 4 bonds. Everybody is stable. Everybody is happy. Okay, so you'll notice over here, I have 3 lines for this because I have 3 central atoms. I have carbon, I have oxygen, and I have nitrogen. Okay, so if we're looking at the carbon, just the carbon, he's got 1, 2, 3, 4 groups around him. So he's tetrahedral in electron geometry. His angle would be 109.5 if your instructor uses the 0.5. There's no lone pairs on carbon. Carbon has no lone pairs, so his shape stayed the same. Okay, and there's only one choice of whether it's polar and what its intermolecular forces are. We'll do that at the end. Okay, so now we look at oxygen here. Oxygen has 1, 2, 3, 4 groups around him. So he's tetrahedral in electron geometry. Okay, he's a little bit less than, whoops, a little bit less than, if your instructor uses that, 109.5 because he's got lone pairs. Okay, he's got the 2 lone pairs. And if you look at that sheet, 4 groups around you, 2 lone pairs and 2 bonds is a bent molecule, right? You've got your atom in the middle. It's a bent molecule. Okay, so my molecular geometry is bent or angular. Your instructor might use angular. Okay, and now I'm looking at that nitrogen there. He's got 1, 2, 3, 4 groups around him. So again, he's tetrahedral in electron geometry. He's got lone pairs, so he's a little bit less than 109.5. He's got the 1 lone pair. Remember, if you've got the 1 lone pair, you're that pyramid with 3 groups on you. Okay, so that's your trigonal pyramidal. Okay. And is he polar? Well, let's see. So we already said we know that hydrogen bonding, hydrogen's bonded directly to a nitrogen, is definitely polar. Okay. And if we did the numbers, carbon is bonded to oxygen, carbon's 2.5, and oxygen is 3.5. That's 1. That's definitely a polar bond. The carbon-oxygen bond is polar. The oxygen-nitrogen bond is polar. The nitrogen-hydrogen bonds are polar. So you absolutely have at least 1 polar bond, and it is not symmetrical. So without a doubt, that is polar. Okay, which makes it soluble in water. And if we're looking at the main intermolecular force, it's that hydrogen bonding that's going on there. Remember, if we're looking at the strength, ionic is the strongest, then hydrogen bonding. That is its main intermolecular force, hydrogen bonding. Okay. Let me look at what else we've got here. Okay. Oh, let's do one of these ions. Okay, so we've got ClO4 with a -1. Okay, so counting our valence. Chlorine is a halogen, so he has 7. Oxygen, oxygen has 6 each. There's 4 oxygens, so 24. Okay, so I'm not going to worry about this one yet. We're going to do that 1 valence electron, that 1 extra charge in just a second here. Okay, so if I look right now, I have 31 valence electrons. So you know there's a problem there because you know electrons pair up. They're always in pairs. So if you have an odd number of electrons, you did something weird. Okay? But I'm going to go ahead and do this without that extra electron and show you why we need that extra electron. Okay? So choosing our central atom, remember multiples go on the outside. So chlorine's going to go in the middle. I'm going to bond his 4 oxygens to him. Okay. So I'm going to count my electrons used in bonds. 4 bonds is 8 electrons. Okay, so what is that? 23. So I've got 23 valency electrons left to put as lone pairs. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23. Okay, so you see that oxygen does not have an octet. Okay, and you can't take an electron from anybody else because then they wouldn't have an octet. So this is why that gains an electron from the universe, is in order to have an octet. So he's got 32, we would have had 24 here to put around. Okay, and because this is an ion, there's a rule with ions, is you have to put it in brackets and put its charge on the outside to indicate that it is an ion. Okay. So now if we're looking at number of electron groups around the central atom, there's 4. So he's tetrahedral, making him 109.5. There's no lone pairs. So his shape just stayed the same. Okay, now this up here is polar, nonpolar, or an ion. He's an ion because he's got a charge. Okay, ions are charged. So his main intermolecular force is ionic. Okay, and for you guys right now, as far as you're concerned, ionic is soluble in water because it's got a charge that's as polar as it possibly gets, is to have an absolute charge. So that is definitely soluble in water. Okay. Let's do one more and then we might just call it good. Okay, so let's do this one. Okay, so I'm going to do the CH3 CHO. Okay, so counting our valence electrons, carbon has 4, each hydrogen has 1. So for those 3, I have 3, carbon has 4, that hydrogen has 1, oxygen has 6. Okay, so I've got 18 valence electrons. Okay, so we're going to choose our central atoms. Well, carbon is going to be in the middle. Both of those carbons bonded to each other in the middle. Okay, and these 3 hydrogens are written behind that carbon, so they're bonded to that carbon. This hydrogen is written behind the carbon, so he's bonded to the carbon. And that oxygen is bonded to the carbon because he's drawn behind that carbon. Okay. Okay, so counting our electrons used in bonds, I have 1, 2, 3, 4, 5, 6 bonds, 2 electrons per bond, so 12 electrons. I've got 6 left for valence electrons. Okay, put them around our outside atoms first to form an octet. So we put those 6 on oxygen. Okay, and you see everybody's got an octet. Everybody's got what they need. Oh, except carbon, right? This carbon, that second carbon, does not have the oxygen, the electrons that it needs. Okay, and following the honk rule, oxygen really likes the 2 bonds, right? So I'm going to take 2 of those electrons and share them as a lone pair. Okay, so now oxygen's got his 2 bonds, 2 lone pairs, carbon's got his 4 bonds, hydrogen's got his 1 bond, everybody's got an octet, and I've used my 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. Okay, so we've got 2 central atoms. Okay, so if we're counting, oops. So number of electron groups around the central atom, that first carbon, we're doing the first carbon first. So it's carbon 1, oops. And that's carbon 2. So carbon 1, carbon 2. Carbon 1 has 4 groups of electrons stuck on 4 sides, which makes him tetrahedral. Okay, there's no lone pairs on him, so his bond angle is 109.5. Okay, he's got no lone pairs, so his molecular geometry is the same, tetrahedral. Okay. Carbon number 2 here has 3 groups around him. Okay, 3 groups is trigonal planar. Okay, trigonal planar is 120 degrees. There's no lone pairs, so it's not less than. There's no lone pairs on that central atom, so his shape stayed the same. Okay, so now we're looking at, is he polar or nonpolar? Okay, so we know carbon-hydrogen bonds are nonpolar. We've already decided that. Carbon-hydrogen is 0.4 nonpolar. But carbon is 2.5 and oxygen is 3.5. So that difference is 1, definitely a polar bond. So I have a polar bond in there, making it a polar molecule. Okay, its main intermolecular force, okay, it's not ionic, and I do not have hydrogen bonding. That hydrogen, there's no hydrogen bonded directly to the oxygen. So it's not hydrogen bonding. So your next option is dipole-dipole. If it's polar, it's dipole-dipole. If it's non-polar, it's London dispersion. It's polar, so it's dipole-dipole. And if it's polar, it is soluble in water. Okay. So, yeah, I think I'm going to stop there for the day. If you have any issues or questions or want more work on this, go ahead and email me to set up a session and I would be happy to help you. So that's Lewis dot structures along with polarity and intermolecular forces and VSEPR. So have a great day.